In this series of presentations on population genetics and allele frequencies, the gene pools, I've been using lactose tolerance as a case study. In this presentation, I want to use my imagination a little bit. I want to talk about a number of scenarios that could potentially apply to lactose tolerance. We know that certain populations have undergone natural selection for an increase in the frequency of lactose tolerance genes. I just want to make up some stories about other ways, other forces that could potentially impact the frequency of lactose tolerance genes, just as a way of showing how these other processes could also change the frequency of these alleles. So in previous presentations, we've talked about genetic drift and how in the absence of natural selection, the frequency of a lactose tolerance gene could bounce around just depending on who lives, who dies, who happens to marry who, what genes they pass on to their offspring. And it's possible even for an allele to become fixed, even if it's just genetic drift that's driving it. Also talked about natural selection, positive selection, and for the big L allele, negative selection against the little l allele. Over time, we could expect that if the big L allele and those who can digest lactose is beneficial for fitness, that the big L allele will fix at 1, the little l allele will decline to 0. Now I want to talk about some other possibilities that could, in theory, happen. And we'll talk in terms of a hypothetical population of Fulani herders in West Africa. So we can imagine that even though there's natural selection, even though it's good to be able to digest lactose and natural selection is acting towards the benefit of those who can digest lactose, immigration can also shape allele frequencies. So let's say that a group of Fula settles in a village and intermarry with wolves who are all homozygous recessive. So the wolves start off homozygous recessive. They lack the ability to digest lactose. They're all homozygous recessive. And then immediately the migration in or the immigration in of these Fulas and their integration into the community would immediately increase the frequency of the little L allele, and it would decrease the relative frequency of the big L allele. And that's a superficial change at first, especially if they just move in and no one has married or had children yet. But we'd still consider that a form of evolutionary change at the population level. It only really becomes interesting when they start intermarrying and then they start producing heterozygous children. And then the frequency of heterozygotes increases and the allele frequencies start changing as people who are half Wolof, half Fula, those heterozygotes now can digest lactose and their fitness can benefit from that. Totally made up situation here, except for the fact that Fula individuals historically often have settled in Wolof villages and intermarried. So also, non-random mating is another way that we know allele frequencies can be impacted. So let's imagine our Fula group settles in this village, but they don't intermarry, that they just marry with other Fulas. So they're living there, they're sharing space, but they're not intermarrying. So if you calculate the allele frequencies at the village level, you're going to see a mix of the alleles. But however, the homozygous and heterozygous individuals from the Fulas are not intermarrying and producing offspring with the Wolofs, and so those alleles are not going to be showing up in the Wolof population. So the relative frequency of the big L allele and the little L allele in the Wolofs and Fula are going to stay the same. You can also imagine a population bottleneck. Let's say there's a drought. It reduces the population size in a village of Fulas, reduces the population size and birth rate. And just due to random chance, the L allele disappears from the population. All heterozygotes and homozygous individuals just randomly happen to be the ones who died during the drought or produced the fewest offspring. This is a population bottleneck. The big L allele can completely disappear quite rapidly due to a bottleneck effect. Could also be a founder effect. Founder effects and bottlenecks effects are very similar. They're both a rapid form genetic drift. So you can imagine that a group of phula that are mostly little l, they travel to a new location and form a settlement. If all of them happen to be little l, then all of their offspring are going to be little l, and the big L allele is going to be rare or absent from that population until it's introduced by mutation. So that could be a hypothetical founder effect. And in both of these cases, in the bottleneck, after a bottleneck, perhaps the little allele could be reintroduced due to mutation or due to later immigration, or in this founder effect example, perhaps the big L allele could be, I might have said little l here, but same thing. For both of these examples, immigration and or mutation could reintroduce the missing allele. Another thing that is known to happen, I don't know if it ever happened with lactose tolerance, but the direction of selection could change, or the strength of selection could change. So imagine that our phulas settle in with a tribe of wolves and they intermarry. And actually, the wolves are really good at farming. It's easier to get your calories from farming than it is to get your calories from milk by herding. And so if it's energetically costly to make the lactase gene, and it's energetically more costly to be a herder than to be a farmer, then there will actually be a change in the direction of selection. Or a weakening of the selection for lactose tolerance. It won't be as important. The difference of survival or offspring production for those who are lactose tolerant will change, and selection will change. This probably shouldn't be called the direction of selection. This would more accurately be referred to as the strength of selection. To have an actual change in the direction of selection would mean that it is advantageous to be lactose intolerant, that it's actually those who are lactose intolerant have better fitness. Could maybe imagine a circumstance where that can happen, but I don't think so. So this should probably say the strength of selection. So already stated, mutation can reintroduce allele. So if our little l allele is totally absent, our big L allele reappears. Mutation can reintroduce it. It can make a few copies, and perhaps if the direction of selection or the strength of selection changes, then that allele, once reintroduced by mutation, can increase in frequency. Can also increase in frequency due to genetic drift. But this often happens. An allele that is disappeared from a population can be reintroduced due to mutation or immigration. Also, directional selection can go in both directions. We've talked about before. We can talk about directional selection for the big L allele. We can talk about directional selection against the little l allele. And we can talk about a change in selection. If for some reason that it was advantageous to be homozygous recessive, selection could change, could favor the little l allele. I'm not sure exactly why this would happen ecologically, but it's possible there could be selection for being homozygous recessive, for being lactose intolerant, and then that would cause the little l allele to increase. So, an interesting fact about allele frequencies. They often change all the time. They change due to drift, they change due to immigration, to mutation, to natural selection. All of those factors, allele frequencies are constantly changing in a population. If all of those forces of evolution stop acting, allele frequencies won't change at all between generations. The change in allele frequency will flatline, and you will see no change over time if all forces of evolution stop. So if there's no selection, no genetic drift, no immigration, you will see constant equilibrium. And we call this Hardy-Weinberg equilibrium.